Good morning, and thank you for joining us today for our Rapid Shutdown webinar. If somebody out there could just raise their hand on the question button there real quick, and we'll make sure that you guys can hear us. We'll go ahead and get started. Perfect. All right, thank you for joining us. I'm Sue Cole, Midnight Solar's North American Sales Representative. I'm here with Ryan Stankovitz, Head of Technical Sales, and he's going to go over a little bit about the MN LSOB Rapid Shutdown line for you today.
Thank you, sir. Hopefully everybody can hear me okay. We're going to talk about just the new little SOB, little shut-off box, and how that works for 2014 and 2017 NEC. Bear with me here, and I'll get this going. So the first thing, for those of you that aren't familiar with Midnight, I just love this slide. It kind of shows what Robin's mind really looks like. Hold on, I'm not showing my screen. There we go. Now you should all see my second slide, hopefully. This slide I just love because it really shows what's going on in Robin's mind, and it's who we are. We make stuff, wind turbines, breaker boxes, charge controllers, lightning arresters, just a little bit of everything. As Roy, the head of our technical support sales department, always says, we make the stuff that goes with the stuff that goes in between the stuff that you already need and have. So this product line consists of 5 different items. Basically, on any system, you'll have 2 items. You'll have a receiver and you'll have a transmitter. As you can see here, we have a 600-volt receiver. We have a 1,000-volt receiver. We have a AC transmitter and a DC transmitter. We also have a unit called the bleed down unit, and this is useful for inverters that don't meet rapid shutdown spec. We'll talk about that a little later, but it does have the transmitter built in. So here's just a little bit of a, drawing of how this actually works. This is a dashed box over here on the left, and you guys can't see my hand, but I'm pointing to this one over here where my mouse is. This would be a solar array. These are your panels in series. There could be, however many panels you need to get to 600 or 1,000 volts. And essentially what this is doing is this box, our little SOB, is breaking this conductor right here, which is disconnecting the string from the last module if it's using it for 2014 compliancy. 2014 basically is only talking about outside the perimeter of the array, dropping below 30 volts in 30 seconds. Now 2017 NEC, which will take effect in January of 2019 for a lot of us, will require this per module basically, because we have to make sure there's not any greater than 80 volts between 2 conductors inside the boundary of the array, and no greater than 30 volts between any 2 conductors outside the boundary of the array. So this single box right now could be used 1 per string, or it could be used 1 per module if you need to comply to 2017. But nobody should have to comply to that until January of 2019. That was an exception wrote into 690.12. Over here on the right, this is your inverter. Typically, this will go right inside the inverter. We'll show that a little later. But in most cases, you can use the DC transmitter in a grid tie inverter because it has a DC power available in the wiring compartment. And that way, when you wire it up that way, disconnecting the AC to the inverter shuts the whole system down when you run the system disconnect, which also shuts down the receivers. So the way these work basically is the transmitter is down on the ground. And as you can see in this drawing, the positive wire goes through the core in the transmitter. And that induces a power line carrier signal onto the PV wire that goes out to the PV array. And these boxes listen for this signal. We call it a heartbeat signal. Some call it a keep alive signal. But the thing to know here is that it's a fail-safe signal. So if this box does not get that special signal, it's going to shut off and assume that you wanted rapid shutdown. So it's always going to fail safe no matter what. This is the same drawing. We're just showing the AC transmitter. You could wire it up to the AC terminals in a grid tie inverter. So if you had a Fronius inverter, for example, and didn't find DC inside the inverter, you could connect the transmitter right to the utility AC power in the inverter wiring compartment. And then when you run the AC disconnect, it would shut off the rapid shutdown. So this one here is showing it actually installed. This is a inverter with 6 strings coming into a combiner, Fronius inverter. They have the combiner built into the inverter right here. you'll see all 6 positives going through the one toroid, and then you'll see the transmitter wired up over here on the left. And that way, when you run the disconnect on the inverter, it initiates rapid shutdown and shuts down the transmitter. Basically, this was designed to work with all grid tie inverters. At the moment, we're saying it's not designed for charge controllers because charge controllers create a lot of noise, which will mask that signal and give you a lot of false shutdowns. We are working on a filter box for most charge controllers that should fix that. Keep that in mind, and if you have an off-grid scenario and you need it, reach out to me or Sue or Rachel or any of us here, and we'll let you know where we are on that filter. That will probably be built right into some kind of bleed-down box, my guess. We've personally in our lab have tested the ABB, SMA, Solarius, Aurora, a bunch of different inverters. We worked really closely with Fronius because we found they had the most difficult arc fault to not trip. So that was probably the biggest challenge about anything PLC driven is no fault strips on somebody else's arc fault. And working on the SunSpec panel as well to create this standard, I can tell you that was really one of the biggest challenges every manufacturer is going to face is the arc fault nuisance strips. As it says there, the hot and cold temperature testing has been proven very reliable. These have been out in the field at least a couple of years now. Some pretty hot environments, some pretty cold environments. Everything's working perfectly. We do have a factory monitored burn-in rack. Not sure why we call it factory monitored, but just know that we have a burn-in rack that does all the final test and programming for all of these, so they're not just simply tested and shipped. We run them through a pretty rigorous set of testing so that you don't have to take your modules back off the roof. Something we were really concerned about is as power electronics manufacturers, we've always sort of shied away from electronics on the roof just because it's more work for you guys to get up there and change them when they fail. And anybody that makes electronics and tells you that they will have no failures is lying to you because we all have some somewhere. And you start doing these for 2017 compliancy where one per module, it gets to be a lot on the roof. So testing, burn-in, that was very important to us to make sure we got them as reliable as completely possible for you guys out in the field. And they are UL listed 1741 by TUV and CSA C22.2. So now we'll go a little bit down into each one and what the differences are between them. As I said, we have 2 receivers. The receiver is the piece that goes in the PV array that does the disconnecting of the positive leads to bring the voltage down where we want it. We have a 600-volt receiver, as we're showing here. This can be used for string level, one at the end of the string to meet 2014, or it can be used one on every module for 2017. One of the big takeaways here is to remember there's absolutely no additional wiring. These just plug in right at the array. They mount right to the rails. You can see with a little hole in the top. And once you hook the transmitter up, you get that PLC signal. They all turn on, and everybody's happy and you're making power. The other good thing about that is a potentially dangerous array at 1,000 volts or 600 volts. By using these, you're limiting open circuit voltage while you're working on it. No voltage is going to be present. So you make it much more safe installation, or a much safer job site, if you will, for your employees while you're installing these. The 600 volt will dissipate about 1 watt at 10 amps throughput. And the other thing to note here as you start seeing more and more competition to this product come out, one of the big challenges is because this is powered by the actual individual PV module, was how much voltage do we have present and how do we make this run in shading scenarios, etc. And the engineering department was able to get this to run all the way down to 3 volts. So as long as that module that it's connected to can produce 3 volts, it's going to stay working. And as most of you know, it takes a lot of shading to get below 3 volts, so we're not too worried there. 12 amps max throughput. That's a big one. We've had a customer that thought they would save some money and use 1 for 2 strings because NEC sort of allows you to parallel 2 strings with no fusing. And they use the Y connector, MC4 connectors, and end up putting about 20 amps through one of these, and it is not designed for that. So remember that 12 amps maximum throughput. It is completely potted of a soft clear silicone. And there are LEDs on the board to show you status. One will come on where it's getting the keep alive signal, and the other one lets you know it's got power. And they're both visible through this clear bottom where the wires come out. Easy diagnosis, if you will. And temperature rating, -40 to 80 C. The device itself can go to 90 C, but the MC4 cables are limited to 80 C. So that is the temperature range, -40 C to 80 C. Here's just a dimensional drawing of it. Not much I can add to that. It's not very big, as you can see. It's about 3 1/4 by 4 inches, and just about an inch thick at its thickest point. But it does mount nicely up on the module, right to the rail. And then we have the 1000-volt receiver. I won't spend a lot of time on this because it's pretty much exactly the same thing. It dissipates a little bit more wattage at full load because of the voltage, but it's other than that, it's the same. It has the same 12-amp maximum throughput, all the same LEDs. It is a little bit different case, as we'll see in a minute here, because the components are a little bigger, spacing a little bigger for the 1000 volts, but this will work with 1000-volt PV arrays. It's probably important to point out too, while you're looking at this dimensional drawing, these are just shut-off boxes. These do not give you any monitoring or any optimization, just so we're clear on that. We do get that question once in a while if these are optimizers, and they are not. They are just a simple switch, which keeps the electronics components to a minimum, and I think makes it more reliable as well. But here you can see the package is a little bit different size. Not a lot, but a little bit different size. A little bit bigger, just for the electronic component spacing. So we'll talk about transmitters a little bit. The transmitter is basically limited to about 75 amps. And with that, we recommend 6 strings maximum because of the 12-amp limit. As long as you're not exceeding the 72 amps, you can push as many PV positive wires through that as you want. So if you had a module that was 8 amps short circuit current, then you can do, like I think 8 of them. Math is not my strong suit today, but you could divide that 72 by your 8 amps short circuit current. This says tested to 5 strings. We've tested it to 7 actually with no problem. We're working right now to do a larger transmitter that will do more commercial scale installations where you can get maybe 15 or 20 PV wires through it. So keep an eye out for that. Module level shutdown, we've tested 12 in series, 36 total in 3 strings. And I don't have a picture of what we call the engineer's homeless shelter. Engineers are kind of fun to walk around. So they've taken this building and built it with an angled roof to put all their PV modules on. And being engineers, they've put rugs in it. They've put, radios and TVs and everything else. So we joke and call it their homeless shelter. But that's what they have on there, is I think about 36 modules total. The module level shutdown is actually much easier to do than string level. We will most likely be releasing some new product first of next year that will be more tailored for module level shutdown. When you do a string level shutdown device like we were just looking at, you have to have the device capable of handling the voltage of the whole string. When you do module level, the device itself only has to handle the voltage of the module it's controlling. So that makes a big difference. Like we say, it can mount inside the inverter wiring compartment. PV plus wire goes through the toroid. Same thing, it's encapsulated with that soft, clear silicone potting. The LEDs show through the encapsulant. So similar to the receiver down in here, you're going to have an LED that will let you know this is actually transmitting. So if you're not getting any voltage from the array, you check and see, is my LED on? It's not. Why is it not on? Oh, I don't have the power hooked to it, or whatever the case is. But it's just easy troubleshooting. -40 to 80 C ambient max, just like the receivers. And 1.5 watt maximum idle power on the DC. As you can see, it's fairly tiny. Not interesting. They don't have a dimension on the overall height, but as you can see, it's about square. So we're going to call it about 2 inches square, 2 1/4 inches square. So it tucks in most wiring compartments very easily. If you have a charge controller, it might be a little tougher once we get it to work with charge controllers, which is why we'll most likely build it into a filter box, just like the bleed down box we'll talk about in a little bit. So this is your AC transmitter, and pretty much exactly the same thing as the DC. Not a whole lot of difference, except for it takes AC in instead of DC. This will take 90 to 305 volt AC. So you could tap off in your 240 volts in your grid tie inverter, or if you've got three-phase, you're doing a three-phase inverter, you can tap your 208. Just gives you some flexibility. Other than that, all the same thing, all the same transmitting power, etc. And as you see, because it is AC, it has a power supply inside it, so it gets a little bit bigger. This one's about 4 inches wide and 2.5 inches tall. So the bleed down box. The bleed down box was designed for inverters that have input capacitors that don't bleed down in the 30 seconds. Pretty much any new inverter being built moving forward will most likely be rapid shutdown compliant. But if they're not, then the bleed down box, what that does is when rapid shutdown is initiated, it will then discharge the capacitors into some resistors inside the box. And it also has the transmitter built inside the box. So this box basically requires, the 240 volt AC from your grid tie inverter to power it. And anytime the 240 volts goes away, it goes into rapid shutdown and shuts down the receivers on the roof. These numbers you're seeing up here really don't apply in general to the bleed down box. These are left over from the transmitters we talked about earlier. So we know it'll do 7 strings, and 15 in series is not a problem for module level shutdown. This typically wants to go as close to the inverter as possible, just because you're disconnecting those wires from the capacitors and letting them bleed down. And the same idle power as we talked about before. All the boards in this are conformal coated, and the temperature range is the same. So the whole product line is rated for -40 to +80, basically. And there's a dimensional drawing on that. As you can see, it's somewhere around, looks like about, engineers, you have to love them. Okay, right here, 6.38 by 9.92. So 10 by 6.5 roughly, and about 5 inches thick. And this is just a line diagram of what that would look like. This also shows you the inside of the box. These terminals are in parallel, so that if there is a question, like on the Fronius inverter, we showed the transmitter and the AC wiring is parallel with the conductors coming in from the residence. And that's most likely not going to be legal in the Fronius inverter because the terminals aren't rated for double lugging. So you'd have to use some kind of thimble or something like that. But in the bleed down box, you bring your utility power into the box, come out of the box, and go back to the inverter. So you have that double sets of lugs to make it easier for you. And of course, all your PV wiring goes through it and ground. That's basically showing the interconnection between the inverter there. And that's just an exploded drawing of it. So a little bit about the backstory on this. This is something we've been working on pretty diligently for a while. We saw this coming when 2014 NEC was written. We knew the next step was going to be more module level electronics. So we've been working on this for, I'm going to say probably 4.5, 5 years actually total, but physically testing in the lab for about 3. We've had field testing ongoing for close to 2 years. With components and encapsulation, a lot of that was done in conjunction with Dow Chemical. We started this project. We were fast-tracking this particular device for Dow for their solar shingles. So they did a lot of legwork for us on potting compounds and stuff like that to really make sure we maximize durability. One of the issues you get into with potting is the potting material is too solid. With thermal expansion and contraction, you start ripping components off the board. So that was nice to have their resources available to us to help us determine the absolute best potting compound. Other than that, like I say, all the components are used below their ratings. Nothing's being pushed to the limit. The MC4 cables are the limiting factor on the 80° C. And the internal components, as I mentioned, still have margin on that. I think we've talked about most of this, but essentially, they're designed to mount to the rail. Plug your inverter in just like you would a microinverter or an optimizer, and build the rest of your array. The connectors are made by multi-contact, so they are true MC4. Not sure that's such a problem in the US, but in Canada, I know they're very enforceful on the mixed brand connectors. So if the module has MC4, you must use MC4 extension cables, or if they're Amphenol in the module, you have to use Amphenol and extension cables. So this particular one does use MC4. If we find that there's a lot of Amphenol modules out there, we could build a model with those connectors as well. Just we found in our research that most modules use MC4. The transmitters, as we mentioned, designed that they could be put right inside the wiring compartment. They could be put on a secondary box if you wanted, or in the disconnect on an inverter. We've already talked about the bleed down blocks needing to be near the inverter. And I don't know, as we talked a lot about NEC, but essentially 2014 690.12 is basically saying that anything outside the boundary has to drop below 30 volts within 30 seconds. Inside the boundary can be whatever voltage the PV array is listed for. Now that, something that to take note on though is that 2014, if you have a code book, it's going to say 10 seconds on 30 volts. But there was a change approved to that allows solar system get up a ladder and cut a hole in the roof within 10 seconds. 2017 is module level shut off. That's going to be an interesting one there. And when it come down to that, they reduced the parameter. I think it was 10 feet for 2014. So if you do a line outside the solar array 10 feet in any direction, anything outside that had to be 30 volts. Anything inside was what we call uncontrolled. In 2017, we reduced that to a foot. And anything inside that now is also controlled and has to drop to 80 volts, whereas anything outside has to drop to 30. So that's where this is being, what's driving this, I guess you would say. So everything we have here meets all the requirements for both NEC code cycles. Shading in low light, we talked about that already, about how hard it was to get the power supply to run down to 3 volts, but that's needed if it's a really cloudy day or there's a lot of shading. We want to be able to maximize the on time of the array. You don't want a shut-off box that's self-powered that has to have 100 watts going out of a 200 watt module, because then if it's below that, the whole array is down. So we took a lot of pains to get that power supply down to 3 volts, which pretty much is no power available in the array. The goal was to take a 5,000 watt grid tie inverter and make sure it's on when there's 10 or 15 watts in the array, and that does work well. So we've maximized that so you won't lose any harvest due to low light or shading. And that's something to look at in the competitive products too, is what is their, what's some minimum voltage they're going to turn on at, so you don't lose a lot of production on cloudy days. Because we all know that pure sun is not always the normal. You can have a lot of days where there's clouds and stuff. And everything is automatic. That's the other thing to remember about this. As long as there's power applied to the transmitter, the receivers are going to turn on. There's nothing else to do. There's no resetting it. If you're familiar with our original rapid shutdown equipment, the birdhouse, when you do initiate a rapid shutdown, then you have to go back and actually, reset everything to get it to turn back on. So this one is all automatic. We talked about this, arc fault. That is a concern. That was a big concern for us on the SunSpec panel. Just nuisance trip of arc fault on everybody's different inverters. And we've done a lot of testing on that. And I don't know what everybody out there has found, but we found Fronius to be one of the most delicate inverters for fault stripping. And that was our biggest challenge to make work with PLC. And we've now got that working flawlessly with no problems at all. And we've beat this one pretty good. Just know it'll meet 2014 and 2017. So moving forward, 2019, January of 2019, we all have to comply to module level shutdown. Several years ago, a gentleman from Fronius reached out to me and a few others and said, we should have a standard so that company A's inverter will talk to company B's rapid shutdown device, and so on and so forth. So it was determined quickly that SunSpec seemed like the right organization to hold that standard for us and help. And we started a work group to build the standard. And I think it's pretty cool because the industry is actually finally going to get some stuff that's standardized. So if you get a furnace inverter that has SunSpec compliant rapid shutdown built in, and you get a Midnite little SOB that has SunSpec compliant rapid shutdown built in, the two are guaranteed to talk to each other. There's no concern on your part about, intermixing brands. And that's going to be really, really big for the industry, because I think that's going to help drive lower cost solutions for this, which was something we were on the SunSpec work group, we were very concerned about, because you start adding electronics to every single module on the roof and you're adding cost to a job rapidly. So on that front, MidNite is working with Texas Instruments on their SunSpec compliant chips. We've got every module in the homeless shelter is running those now. We're working really well with that. It looks like it's going to reduce cost for 2019 compliant product, and it will also be SunSpec compliant, so that's going to be pretty cool. We will continue with our non-SunSpec version for right now for off-grid stuff after SunSpec takes hold, if it makes sense viably. But we have to look at all of that and say standardize on a single product, and if SunSpec actually takes off and then manufacturers all start following that, which I believe they will, we will of course follow that too to make life easier for all you guys up there on the roof. That's pretty much all I have on that. It's a pretty simple product. I mean, the big takeaways, if you remember, it's all automatic. There's no extra wiring. As long as the transmitter is transmitting, the receiver will receive and turn on. There are a couple things to be aware of with any PLC-driven device like this, be it ours or NEP's or somebody else's. And the big things that you're going to run into are what we call crosstalk, and the other one is the limitation of the transmitter. So you heard me say in our case, this current transmitter is good for about 72 amps. Once you exceed that amperage, the core that the wires go through does what we call saturate, and the signal no longer can be transmitted. So that's something that you want to look at with any manufacturer's device, is what is their maximum number of strings that can go through a device. And crosstalk is another big one that will get you in trouble. If you run, say, a rigid conduit or a PVC conduit or any conduit from an inverter up onto the roof, and let's say you've got 3 inverters and you run all 3 wires in the same conduit up onto the roof, those transmitters will then mix in that conduit just from induction from one wire to the other. Then the signals get lost. So anybody that's played in radio, ham radio, or anything like that will know that if you get 2 signals a little bit out of phase with each other, they cancel each other out to a point. So that is an issue with crosstalk, and you do need to be aware of that with any manufacturer's device that runs PLC, not just ours. So it looks like, sorry about that. Looks like we have a few questions. I will let Sue read the questions, and I'll do my best to answer.
All right, so Carlos is asking if this will be available on the webinar. And we certainly can make that available to you if you want to just shoot us an email after this and to webinars@midnitesolar.com. We'd be happy to get this presentation over for you.
Okay.
Do we have any other questions? Give everybody just a minute more in case they're slow like that typing like I am, and then we'll move on. All right, looks like we don't have any more questions. Thank you all so much for joining us today. It's been our pleasure, and we hope to see you again at another future webinar.